So, welcome to this week's Origins colloquium. It's a great pleasure to welcome Tom Megeth to give us a talk this week from University of Toledo. Tom received his PhD in 1993 from Cornell. He had positions at the Max Planck Institute for Radio Astronomy, MIT Haystack, and the Center for Astrophysics, Smithsonian Center for Astrophysics in Cambridge, Massachusetts, where, as I understand, you were part of the IRAC instrument team building the camera for Spitzer, which was, of course, very successful. More recently, Tom has been one of the pioneers using James Webb to study star formation in our galaxy, and I think that's what we'll be hearing about soon. Of course, in between then was leading one of the key projects with Herschel, studying star formation, the HOPS project for protostars in Orion. So we look forward to your talk, Tom.
All right. Well, thank you, Jonathan, and thank you for inviting me to give this talk. Um, so hopefully, as I mentioned to Jonathan, it's the beginning of classes and everything is very chaotic here. So I have sort of put together a presentation, but obviously, if there's any questions, I'm things that I left out, things that I sort of glossed over, please ask me during or after the talk. So what I'm going to give here is really the product of a huge team effort. I'm going to concentrate on two JWST programs that we were very fortunate and lucky to get through, one in cycle one and cycle three. And most of the work that I'm showing, including the image, which is hopefully in front of you, which is NIRCAM images of the OMC23 region of Orion, showing lots of protostars and outflows, are the work of a huge team, of which I feel like I've contributed maybe minimally sometimes. And this image together was basically made by Rob Gutermuth. I'll talk more about it later. All right, let's see. Okay, so well, this is sort of a famous image of the HH211 outflow from the Nature paper, and I actually superimposed over it one of my favorite cartoons of a protostar from Robert Hurt. This, of course, is from Ray 2024. And I just put this up there. I'm hoping that, being that this is the Origins colloquium, I don't really need to motivate why we study protostars, but I often do when I give talks, because I think in a lot of places people have only a vague notion of what a protostar actually is. But I think what's really important is that the processes within 1,000 AU of this protostar, which include an infalling envelope, an accretion disk, an accreting protostar, and then the jets and the winds launched by the disk, basically shape the IMF and regulate star formation in molecular clouds. And so this little region within 1,000 AU contains a lot of essential physics that we need to understand cosmic evolution at large and the origins of everything from planets to galaxies, if you ask me. And so that is sort of the starting point for a lot of these investigations. And so I'm going to sort of organize this a little bit by the proposals that we wrote. And so let's see. I'm going to start by talking about the first program we did, which was a 65-hour cycle one GO program called Investigating Protostellar Accretion. And it is an IFU study of 5 protostars they're not edge on, but they are inclined. And they covered basically the mass spectrum as measured of the central masses of the central protostars, mostly measured by Keplerian motions. And it includes protostars that go in mass from about 0.15, IRAS 16253, which is that's in Ophiuchus, to basically about 12 solar masses, which is IRS 20126, which is basically in the Cygnus X region. And you can sort of see the sample that we chose here. And you can see actually near spec imaging that was put together for Fetterman et al. 2024, showing both scattered light continuum in red, molecular hydrogen emission in green, and iron 2 emission in jets. And you're going to see this whole all of these components in much more detail as I give this talk. I should also note that the luminosities of these sources vary dramatically from about 0.16 solar luminosities for 16253 to 10,000 solar luminosities for 20126. So with this 5 stars, maybe it's not representative, but we cover a lot of territory, right? The kind of physics we need to understand the mass function was the hope. Okay. Now, before I talk more about the IPA results, I also wanted to mention the second program that we got through in cycle 3, and this ended up being about 193 hours. So it is a large program. And on the left, you see Spitzer and Herschel images of the Orion Nebula cluster, which we sort of see in the Spitzer data. All the green dots are little young stars. And what the molecular astronomers refer to as the integral shaped filament, which is basically the several thousand solar mass filament that is forming the Orion Nebula cluster that obviously has that integral shape sign. And all those little circles that you see are protostars that have been studied by the HOPS program in Furlan et al. 2016. There's a bunch of references there. And so this northern part, which is actually, I think, the most active from the density of protostars or concentration of protostars, the most active region of star formation within 500 parsecs, certainly, maybe within a kiloparsec. And we imaged that with NIRCAM, and you see the NIRCAM image on the right, again, assembled by Rob Gudemuth. We're missing one field, but hopefully that will show up in the next few weeks. And then in addition to that, we took the 13 class 0 protostars in that field, the ones that you really can't study at shorter wavelengths, and we did IFU studies of those. And so these are the two programs that I'm going to overview fairly rapidly next few minutes. Now, just to give you the spectroscopic view, this is one of the protostars from the IPA program, HOPS 370. It's an intermediate mass object, around 2 solar masses. And Himanshu Tyagi put together this amazing spectrum of the central region. And you can just see immediately how rich the data set is from the IFUs, right? And so these are 2x2 fields that are a little bit wider than many of the fields. And this is just a central position. And you can see that there's many molecular lines. There's also ionic lines, there's atomic lines, and a multitude of ice and some mineralogical features as well. And so from this data, we can, and of course, because this is an IFU, we can make images in each one of these features. And so we have, with the IPA data, we're just having another wave of publications coming out now. We have basically spent the last few years just analyzing these 5 sources, and the complexity of it has been, well, it's both fascinating, but also a bit daunting. So one of the first things you can see, excuse me one second, is the ice features, which you can see if I go back one. You can see there's a multitude of ice features. I'm going to concentrate on the water ice and the CO2 ice, both in the near spec view. The water ice we only get incompletely, unfortunately. The CO2, we focused on the 13 CO2, which is not so saturated, which you might be able to recognize. It's around 4 point something microns there. And here's basically a close-up of it. This is another paper by Himanshu Tyagi. It's actually the same one with the spectrum. And basically, he took the near-spec data and measured the ice absorption against the scattered light nebula of this protostar HOPS 370. And the beauty of this is that you can measure variations in the ice features as you go across these, which you can see on the left are basically the ice features seen at 4 different positions. Right. And what we found is that there's variations both in the depth of the ice, in the aperture that's called 1, which you can see in the upper right. There's actually a hole in the ice. And you can sort of see that in the spectrum called 1 there. You can see the CO2, 13 CO2 there is very weak. But it also shows when you look at the water feature, that sort of sharp peak point is a measure of the crystallinity of the water ice, whether it's more crystalline than amorphous. You can see that there's sort of a peak in the crystallinity. And basically, we concluded from that there was actually a hole or area of low extinction in the envelope right around position 1 that allowed us to see the inner regions of the envelope where the heating of the protostar was processing the ices. And basically, that was responsible for the higher crystallinity. We also noticed ice processing. This is a paper by Minashanti Brunken in 2024 that if you measure in these CO2 features, the 13 CO2, the amount of pure CO2 in it, for our more luminous protostars, HOPS 370 and IRAS 20126, that the fraction of pure CO2 actually goes up dramatically. And that is thought to be due to the sort of distillation and segregation of the ices that are being heated in these more luminous objects. And I just noted at the bottom that we've done a number of papers on ices and various aspects of the ices, and I listed them at the bottom of this. I just can't go through all of these in a 30-minute talk, right? Now, my personal focus on these regions have been more on the feedback, and that's something what the JW is just able to do beautifully. Right. And you can immediately see this when we show the iron 2 maps from MIRI at 5.34 microns. And here are basically 16253, B335, and HOPS 153 are all class 0 protostars. HOPS 370 is a bit more luminous, but it also has a very massive envelope. And so I think all of these are basically in sort of an envelope dominated phase where stellar mass assembly is occurring. And then IRAS 20126, of course, is our most luminous object, basically a high mass protostar. And you can see that one is a bit more complex, right? And I'll address the reasons of that later. But here, by the way, is if you actually sort of scaled them to the relative spatial scales, right? So that because 20126 is much further away, when you put them so that they're all in the subspatial size, it's a much larger structure. And so you can see the most massive objects are also creating sort of the most sort of extended and complex sort of distribution in the iron 2, right? Now, the iron 2 is basically due to shocks inside a jet, so internal shocks that basically can ionize and heat the gas. And what we found very quickly, and this is a paper by Mayank Narang in 2024, is that you can actually measure the velocities of the jets. And so this is the jet at 16253, and the left-hand diagram shows a map of the jet, sort of aligned up and down. And then the middle plot shows you a position velocity diagram in the iron 2. And so you can immediately see a strong shift in the velocity. And then you can basically measure the velocity just by fitting Gaussians to the line. And we can sort of see the blue shifted and red shifted jet. And from that, taking account the inclination of the disk, which we know from ALMA data, we can measure the velocity. And in this case, we get that the 3D velocity of the jet, assuming a 64-degree disk inclination, is about 170 kilometers per second. Now, Sam Fetterman has a paper that was accepted recently. It's going to be on archive any moment now. And we did this for the next three jets, B335, HOPS 153, and HOPS 370. And again, you can sort of see the same sort of structure here where we can measure the velocity shifts between the two jets in the iron 2. And let's see if I go that. We measure the velocities. And again, all of these things are basically measuring shocked gas in jets. That's about 150 kilometers per second. And an interesting question is exactly what's generating those shocks. That's something I don't think is very well understood. Now, you'll notice that our high mass object, one other object that we did is B335. B335, we actually, because of issues with MIRI, the second observation, so he took an observation in NIRSpec, and in the MIRI observations, because there were some issues with I think one of the grading wheels with MIRI, was basically obtained 8 months later. And one of these knots, we see these knots, is basically seen to be moving between the MIRI and the NIRSpec epoch. And so using the proper motions of the knots and the radial velocities of the knots, we calculated a 3D velocity, which again is about 150 kilometers per second. And interestingly, we noticed that this jet seems to be inclined at about 57 degrees, which is actually a much lower inclination than the actual cavity is thought to be. So it's tilted relative to its cavity. And it seems to be also sort of tilting, shifting, processing with time. All right. Let me and now sort of shift, sort of lots to go through here. The most massive object, that's the one we're missing right here. This is 20126. this is the iron 2 map. On this map, we have plotted the position of where the central protostar is, to the best of our knowledge, and two known companions, the north companion and the south companion. And you can sort of see the iron 2 here does not form a nice jet. However, work by a number of the grad students here at Toledo, led by May Higgins and also Sam Fetterman, who's a postdoc now in Naples, we now think that there is basically three outflows in this. This also uses additional data from the ground, but there's basically an outflow jet in the iron 2 from the central source, but then there's also an outflow jet from the companion that overlaps it. And then there's, I think, even a second outflow jet from the companion, which might mean that the companion is a double system that's heading in a different direction. And this is obviously work in progress, but it sort of shows you that even in 20126, which is probably the least clustered, most simple massive star that you can think of, there is already a great deal of complexity due to the multiplicity of this object. All right. Finally, going to the complete opposite end of our mass spectrum, we have IRAS 16253. This is the lowest luminosity source. And for a while, we thought, well, maybe people have thought that this source could be even substellar, but we now know from the Keplerian measurements that it's about I think it's like 0.12, 0.15 solar masses. And it has a very low luminosity. And it turns out that the reason it has a low luminosity is that it has an extremely low accretion rate. And we have measured the accretion rate from this object two ways. Well, once we haven't measured the accretion rate, but we measured the outflow rate in the jet by using the iron and neon lines to estimate shock velocities and pre-shock densities. And we get values of around 10 to the minus 10. And then in a paper that was recently accepted, and I should be going in archive soon, we used OH detections, OH lines towards the center of 16253, which we believe are due to the disassociation of water by UV from accretion shocks from the central protostar. And there's a very nicely argued description of that in the paper. And thus, from the OH lines, from the brightness, we can basically calculate the rate at which UV is being produced. And by comparing that to shock models to accretion models, we can estimate an accretion rate, and it's around 10 to the minus 9 solar luminosities per year. And so this object, even though it's a class 0 protostar, deeply embedded, appears to be in a quiescent state where the luminosity is dominated by its photospheric luminosity, right? And so, but we still see a jet, and as I show later, we still see a wind from this object, even though it is in this quiescent state. So the OH, by the way, this is, I think, the first time that OH has been used as a tracer of UV radiation from shocks and been used to measure accretion rates from a protostar. Now, one of the things that we're very interested in is basically what lowers the efficiency of star formation and ultimately shapes the IMF. How do outflows do that, right? So we know that outflows presumably push back on the infalling envelope. They eject gas, entrain gas, and outflows that are seen with ALMA. We also see these jets, which I've shown you in a previous data, but the jets are all highly collimated. And so this makes us think that there's a wider angle component that we are not seeing. Now, if you look, by the way, I've sort of given this slide in the wrong order. What I'm showing here is on the top, I showed a scattered light nebula for three of the protostars, B335, HOPS 153, and HOPS 370. And the reason I showed a scattered light nebula is basically these are the regions that have been cleared by the outflows, right? So outside these bright illuminated regions is basically the molecular cloud, and inside of it, the gas has largely been cleared by outflows, right? And then presumably there's an entrainment mechanism happening along the edges of these. And all of them show the typical bipolar morphology to some extent, although they're more irregular than you might have thought from very simplified axisymmetric models. But you can sort of see that these are all much wider than the jets, right? So what is the process that's actually entraining gas along the edges of these and clearing these cavities? And that appears to be lower velocity winds. And so in all of these objects, and this is work by Miank Narang, who just has a paper that's submitted, and Himanshu Tyagi, who's about to submit another paper, we basically find that these cavities are filled with warm molecular hydrogen emission. Right. And here you can sort of see that we have the S1 line on the left, and that one literally fills it. There's a little bit of evidence along shocks along the edges, but the emission fills it. It's not strongly Lindbreiten. And we can measure the velocity shifts, again, using MIRI, and show that the typical velocities are roughly around 10 to 20 kilometers per second. Interestingly, as you go to higher and higher rotational transitions of H2, the gas structures become narrower and narrower, and they also become higher velocity. So there's sort of this onion shell, or we call it leak shell structure to this, where the highest velocity and hottest H2 is near the center, near the jet, which I think suggests an interaction between the jet and the overall wind. Now we're sort of Himanshu. This is sort of his thesis work, and he's putting together papers on this, and it's a little bit preliminary. But one of the things we wanted to do was to estimate sort of the mass loss and momentum from the H2 winds, basically by just counting up all the molecular hydrogen that we detect in the cavities, basically using rotational diagrams, and then using the velocities that we measure and the inclinations from the disks to get sort of the 3D velocities of the wind. And what we've done is we've overlaid these on a study by Dan Watson in 2016, where he uses various atomic ionic lines to get outflow rates versus luminosity for protostars. And we have put all of our objects, the wind outflow mass outflow rates versus the bolometric luminosities on this diagram. And so you can sort of see there certainly is a trend with luminosity. As you go higher and higher, basically the outflow rates increase and momentum rates increase. Interestingly, for IRAS 16253, the object that I showed was in a quiescent phase. The mass outflow rate from the wind is orders of magnitude higher than the outflow rate we calculate for the jet. And that's really interesting. We're still, as I said, this is preliminary. We're still thinking about it, but I think it's a fairly well-established result. All right. Well, I have a little bit of time here. Let me just go quickly to the HEFE program. This is the image that I showed earlier of basically, this is a combination of three of our wavelengths, the F210, the 360, and the 470. The 470 is basically centered on the S10 line of molecular hydrogen. And so you can see this is actually rotated 90 degrees. So the filament actually goes north-south, but that's not, it's not well aligned with our viewer here. So you can again see the complexity of this region. This is actually using a different set of filters here, just different colors, but you can see that we have multiple bands. You can again see there's many outflows going many different directions here, and we're sort of working on cataloging those and their morphologies. This is like Himanshu Tyagi put together a nice little sort of montage of the various jets here. I think it's in the S9 line. I said S10 earlier. And you can sort of see there's lots of different morphologies. These are not continuum subtracted. So notice there's scattered light nebula to the center, and there's also stars. But you see evidence of asymmetry, of precession, of what might be variability in the terms of all the little knots and stuff, and also bent jets, and all kinds of just really interesting morphologies, right? Now, interestingly, let me just do a quick digression. One object that we see that we did not get IFU data of is a source called HOP70. It is actually not launching an outflow. You can see that here. But the reason I put this in is you can actually see it in our images here. It is what we think is actually a very envelope-dominated object, like a class 0 protostar, but basically observed at a lower inclination so that we can see through the outflow cavity the central protostar. And the diagram on the left is a diagram that from a paper by Sam Fetterman showing that this object in the little circle actually has a fairly high envelope mass and a fairly high envelope to disk ratio comparable to class 0 objects that we have seen. The interesting thing about this object, and I just wanted to this is like a little advertisement for the thesis of Savio Oliveira, is that whose name I forgot to put on this, is basically we have Igrin spectra in the near infrared of these, and we can basically, from this protostar, which normally for a class zero would be too embedded to really study in detail, we can get very sensitive spectra across the 2 micron range. We can get photospheric temperatures, we can get veiling, we can get the bracket line accretion, and we can actually also get the fraction of the luminosity from accretion. And from that, sort of estimate accretion luminosities and mass infall rates for these objects. And so this gives us a way of studying really deeply embedded objects like class zero objects, actually studying their accretion and not just their outflow. All right. Now, jumping back to the connection between accretion and outflow, this is B335, one of the sources we studied in the IPA study. And this is a slightly complex figure from Sam Fetterman's paper. And what you see in the dotted line is basically the light curve of B335, which was basically underwent a burst while being observed by NEOWISE, which were all the little black dots. And one of the things that's really interesting is whether there's a connection between the knots that people identify in the outflows and accretion events. And Sam had gone through and identified a number of the accretion knots here, and he plotted them in blue and red stars, the colored ones on here. And we see that the knots are not really, they're more frequent than you would expect from bursts. They're separated by decades. And the knots don't seem to have a strong correlation with the actual outburst in this particular instance. So maybe they're a little bit closer together during the outburst, but there's not a strong dependence. On the other hand, there's this object HOPS 383, which is an outburst, was the first class zero outburst ever detected by Safran and Fisher in 2016. And this is an object that basically went through an outburst. Here's a light curve from Zachary et al. 2023 in the lower left, which shows you the IRAC 4.5 micron photometry. It's very sparsely sampled, but you can see it rising in 2004, cresting in around 2010 during the YSOVAR study. And then by about 2016 and 2017, it was on its decline. And by 2019, it was down. So this is about a 16-year-long burst or 15-year-long burst, very luminous, probably a factor of at least 10 in luminosity, sort of like maybe similar to class zero outburst, but observed in a very deeply embedded class zero object. And with our HEFE data, we can actually see, this is actually from a poster that Andy Miller showed at the AAS meeting last week. You might recognize this. We can actually see the outflow from HOPS 383 in the molecular hydrogen lines. This is in the filter right here. You can sort of see a close-up of it, and you can sort of see where the protostar is. This is not continuum subtracted, and you can sort of see a knot and then a second knot and stuff. And one of the things we've been really interested in is, again, do we see connections between accretion outbursts and structures within the jets? And so one of the question is this knot that we see close to the protostar associated with that particular jet? Now, that knot is seen in a range of lines. Here it is seen in iron 2. It's not really like a distinct knot. It's more like a modulated jet with a very sharply peaked region. We see it in ionic lines. We see it in molecular lines. It's very rich. It does look like it peaks at a certain distance away from the protostar. So then the question is, how fast is this jet moving? And what is the dynamical time associated with the jet? In other words, how long at that velocity would it have taken, say, the material in that jet, say at the peak of the jet, to move from the protostar to its current position? And is it plausible that that jet was actually launched during the outburst? By the way, this is just a spectrum of the jet, just showing you again how rich the IFU data is for these sources. And so it's sort of spectacular in these regions, and we're just starting to scrape the surface of this. But particularly the number of molecules that you see from OH to H2, a little bit of water, CO, and everything in an outflow knot. This is subtracted back. We've subtracted out all the other emission. Is beautiful. Now with the iron 2, we think we see both the jet and the counterjet. And so using the methodologies that Mioch-Narang and Sam Fetterman established, we measure the velocity of the jet, and then we use an ALMA measurement um, uh, basically of the inclination, and we calculated what the velocity of the jet would be. And we're still sort of playing with this, so it's a bit preliminary, but the velocity is about 106 kilometers per second. And then you can then use the inclination to get a projected velocity along the plane of the sky. You can measure the distance along the plane of the sky. And you can sort of then basically calculate a dynamical time for the jet or each portion of the jet. And so that's what we show on the right. This again is the work of Andy Miller. The profile you see is basically the profile of the jet, which you can see is sharply peaked. But for the x-axis, we've basically taken the distance and divided by the velocity to get sort of a dynamical time. And then we put to our best of our knowledge, the beginning of the outburst and the end of the outburst relative to the current period. So zero is now. And we can sort of see that the outburst peak is roughly where the outburst began. Well, I should say the jet peak has a dynamical time equivalent to the beginning of the outburst. However, this is the velocity of the shocked gas, and the gas in the jet is probably, almost certainly, moving faster than the velocity of the gas in the velocity of the gas in the jet is moving faster than the shocked gas. And so in reality, this peak is probably within the outburst. And so I think we're sort of concluding or tending to conclude that this feature, this bright modulation of the jet, is indeed associated with the outburst. Although the exact timing is hard because, again, we don't know the velocity of the jet itself. We know only the velocity of the shocked gas. All right, and I think I'm basically out of time here. But here's like a quick summary, and then here is unfortunately, I realize I left off a few people that have accreted to these programs, but this is sort of a list of the team memberships of these programs and sort of a quick summary of the results that I just rapidly flew through. So I'm would be delighted to get questions and stuff about these particular things, and I'm happy to elaborate on anything. Thank you very much for your time.
Great. Thank you very much, Tom. So we have time for questions and discussion here, and there was a great overview of many different things here. Very beautiful data. So maybe somebody in Virginia can help me if there are questions in the room, and people online raise your hands, of course. There's a number of aspects we can maybe go through from the detailed properties of the outflows and the sources to the sample itself, and maybe, I mean, what I was struck by first is, in fact, you mentioned the five first sources. They have a very wide dynamic range in mass and luminosity, but their morphologies and the velocities you were finding in the iron 2 seem all fairly similar. Maybe the high mass one is a little more confused, but the others seemed, if I recall correctly, very, very similar velocities. Is there any hint the velocities get faster as I don't know, the protostellar mass increases, or?
We don't see any dependence. I mean, the sample is relatively small, but you can sort of see that the velocity of the most luminous source here is HOPS 370, which is about it's 320 solar luminosities, and it's like 2 to 2.5 solar masses. And the velocity of the jet doesn't seem to be any higher. We think the mass flow in the jet is higher, but we're having some issues with the measurement of the shock velocities in the jets because it requires um, uh, um, basically argon and neon, the two noble gases, because iron is problematic because the abundance may vary. And the argon line is strongly affected by ice features. And so we're trying to figure out how to correct those. So we don't really have well-established flows, but I think the flows might be different, but the
Mhm.
velocity is not so much.
Well,
As far as we can tell.
the theoretical models of jets, I'm trying to remember now, but surely the terminal velocity, I think, should relate to some multiple of the escape speed from where it's launched, and it's launched near the surface of the star, I guess, or maybe there's a. I mean, are you comparing to X-wind models or any kind of jet models to test these?
In a way, I mean, so if you basically the picture that we favor is that these are more consistent with like a disk wind kind of model. Because the X-wind, the problem is the wide angle component is very high velocity. So you have to find a way. And then the X-wings, I think, also have trouble launching molecular gas. There are ways around that. And so, I think the jury is maybe still out. But these fit very nicely in the sort of disk wind kind of models where we are, the Iron 2 is maybe more from the central jet, central launch from the central regions. You see it in iron because the velocities are really high. And so the shock velocities can be very high and dissociate molecules and such. Um, and then you see launch from larger radii, you see the winds. One of the interesting things is that there's the question of whether these are all class zero objects. Um, and we see sometimes knots of molecules. So B335 and HOPS 370 have knots of molecules and stuff, but we don't see the jets primarily in molecules. They're certainly in iron. And
Mm,
maybe that's just a velocity thing. I know for HH211, there's a different story there. That is a younger source probably than these objects. So there's some complexity there. But I
mm,
think it's a really interesting question, basically, when the molecules show up and what the properties are needed for the molecules to show up. We just
mhm,
see them in the wider angle winds primarily.
mhm,
But I guess just going back to sort of to elaborate too much on this is that there might be sort of like a velocity bias. If there's a range of velocities, maybe that there are higher velocities in some of these jets toward the center part, but the parts that we're seeing might be, that Iron 2 just picks out stuff that's roughly around 150 kilometers per second. There might be some bias from the tracer. That's speculation on my part, but you
ah,
know, uh, yeah.
yeah. So I have many more questions on but so if there are other questions, please, people raise your hands, and if there's anything in Virginia, please unmute there.
Yeah, can I ask a very quick question, Jonathan?
Yeah.
Sure, introduce yourself as well so that Tom knows.
Sure. Yeah, I'm Ryan Boyd, and a postdoc here at Virginia. Thanks for the presentation. I was wondering about the OMC2-3 NIRCAM image. Have you found any new protostars, or when you say you're cataloging all the outflow features, I'm just wondering if you found any new protostars, or if they're all features seen towards the same known sources.
Yeah, there are a few protostars that were not identified by Spitzer and Herschel, mostly because of confusion.
Yeah,
Uh, we've actually seen some of them before in HST imaging, but of course we didn't actually have the spectra. Actually, one of them is actually really interesting. You can sort of see it. I don't know if my cursor is working here,
it's
but it's
working.
just
Yeah.
yeah, it's right next to Hop 70 here. And it's actually not that faint, but the Spitzer data it's just confused because it's so next near a bright source, and you can sort of see it has this beautifully arced outflow coming from it. So that is one. You can sort of see this a bipolar source, but I think that the number that I know of, it's less than 10 in
Okay.
it, right? And so it's not maybe seven or eight. We don't have as the full SCDs, obviously, so it's not a huge number.
Hmm.
Okay.
Let me follow up on that then. I mean, are you able to find binary protostars? Are there any?
Yeah, I mean, Hop 70 is actually a classic example of that. In fact, it's multiple because it's that object you see up to the upper left of Hop 70 is considered to be a companion. That's from the ALMA and VLA work that John Tobin did. And then Hop 70 itself has a companion. We think that the spectrum is dominated by the primary source, but it does have a fairly tight companion that's seen in the ALMA and the VLA data, and also now in some of the near infrared data. And this third protostar may also be a companion. One of the things we're wondering is if it's been sort of ejected from the system. So we do see it. We haven't really. I did earlier papers at shorter wavelengths with Marina Kunkel and others about the multiplicity. John Tobin has it. So we do actually have multiplicity for a number of these protostars, but we haven't all. I think. Of the ones with the IFU data, I have to say I don't remember. There are multiples in that sample as well. We just haven't, you know, the fire hose is on, and we just haven't had a chance to digest all of
So
this.
within the IFU field of view, roughly what is the scale of that at Orion?
Oh, well, it's about 6 by 6 arc seconds, so it's about 2400 AU
Hmm.
side to side. Yeah.
Hmm.
So you can see close binaries in there, and there are some with that in that system. So and yeah, but in terms of I'm trying to remember from all the work that we've done in terms of like picking out the different components. So what a beautiful example of this is a source that hops 87 that we never knew was binary. Um, and it turns out because there was an infrared component and there's a Herschel component, and it turns out that the Herschel component is distinct now from the infrared component. And so there's like a companion that's seen in the infrared, and then the primary protostar is not even really detected. Maybe we detected at 25 microns with MIRI, but shortward of that, nothing. And so that's an example of a really interesting system that we would not have known was a multiple before the Herschel data. But that one is weird because you actually one is actually seen by ALMA and in the millimeter in the far infrared, and the companion is not detected by ALMA. It doesn't have a detectable disk, but is strong, shows strong lines in the mid infrared, and it's clearly a YSO.
Hmm. And how close a separation do you think you can distinguish multiples?
Well, zero point 0.2 arc seconds is sort of our where we would go down to, so that you're getting down to about 80 AU, right? So, you're not really getting down to the peak of the multiplicity probably at
Hmm.
this range. Yeah.
Hmm. Great. Any other questions for Tom?
Yeah. We have another question to Virginia.
Yep.
Hi, Tom. Great talk. Ashish Gupta, postdoc at University of Virginia. I was wondering, like, when you try to estimate accretion rates onto these class zero protostars using, for example, OH, how do you correct for extinction? Because they should
Oh,
be highly extincted.
yeah. That's well, correcting for extinction is a problem with all of our data. And H2, iron 2, and everything. For the OH, it's actually not so hard because you can actually use the OH lines. The idea is that you basically have a rotational sort of a cast. It gets dissociated and then it just sort of goes from rotational state to rotational state as it goes down. And you can actually use the ratios within the OH to determine what the extinction is. So that one is actually relatively easy. And you can sort of see that the OH sort of straddles various extinction features. You do have to assume a dust model, and so we've been using the Pontoppidan model, which has includes all the ices and stuff. So you do need to do that. But because these cover such a large wavelength range with various mineralogical and ice features, you can get the extinction. For the jets and the molecular hydrogen, we actually use the molecular hydrogen data from the cavities to do the extinction, and it's because the S3 line falls in the middle of the silicate feature. And so we do the rotation curves, and then we basically fit it with a two temperature component plus extinction, the rotational diagrams of the H2 to make a map effectively of the extinction. And that's the only way we've been able to find how to do the extinction in the cavities itself. So, but yeah, it's tough. It's
So,
yeah.
so I mean, it looks like this is a PDR in the outflow. I mean, you also mentioned shock ionization as, so what's your sense of, are most of the lines coming from shock ionization, or are there certain lines coming from photodissociation? Can you
So
think?
the OH lines here, we all think is basically due to the dissociation of water, right? So that's basically the model. So you can actually the various spectroscopic signatures, and these are described in detail in Dan Watson's paper, basically point to the fact that you basically dissociate H2, it ends up in a highly excited rotational state, and then it just
Hmm.
sort of cascades downward.
So do you have
And
diagnostics of the FUV field then from these lines, I suppose?
yeah, you can actually basically measure the number of UV photons, the rate of UV photon production within a given wavelength range. Now, the OH for this source is concentrated at the center, and so we're pretty confident that this OH emission is coming from shocks, from accretion shocks. But there's another source, and there's a paper by David Neufeld, where we do see OH, but it's not from the central source. I think there's a thing here. It's actually coming from an outflow knot. Yeah. And there's a paper by Neufeld. Sorry, the slide got sort of messed up a bit when I shifted formats. But there's the OH spectrum is shown here, and it's actually completely consistent with the basically Lyman alpha being created by a shock in the jet, and then that basically dissociating water, and it gives you this very characteristic curve in the OH lines that you can sort of see here, the distribution of the OH rotational diagram, where it basically drops off very rapidly about of n upper 46, 47.
Hmm.
Uh, right. So you can sort of see the OH is in the middle part. I'm sort of going through this fairly rapidly. This is all the OH lines, the OH ladder, and you can sort of see that sharp drop off. So in this case, we think it's an internal, the UV is coming from shocks within the jet.
Hmm.
But in the other case, so it's tricky. And in some cases, it looks like it's coming from the central source. In some cases, it looks like it's coming from the jet, and you have to use the morphology primarily as to distinguish the two.
Hmm. Well, as you
Right?
put the high mass systems, eventually they should be strong UV sources from the star, from the photosphere. Um,
Yeah.
so,
Well, yeah. So that's a really interesting question, and I was going to mention a little bit of that, but I didn't get around to it. We're still sort of milling, but there's not much evidence of UV in the sources, in the high mass source. So, for example, we have bracket alpha. We show a little bit of bracket alpha, but it's sort of in this little peak here. We think it's scattered light from the central protostar that's scattering off of a little crease in the outflow cavity. Uh, the outflow is filled with water and acetylene and all kinds of crazy molecules, but not much OH. So in fact, the OH I think is undetectable. And so it seems like in the outflow, which is primarily molecular, by the way, there isn't much evidence that the UV is getting out. So if there is UV radiation being produced by either shocks or the photosphere of the central source, it is so deeply embedded that we are just not seeing it in the IR.
mm, hmm.
So it's actually this outflow is more molecular and richer in molecules and richer in water than the outflows from the say from the other lower mass protostars. And I think it's just a matter of that to make a massive star, you just need a lot of material, and it's just very deeply embedded. I guess it
Hmm.
could also the massive star is also inflated a bit, from sort of a hot accretion kind of scenario. But I don't know. Yeah,
Right, right, yeah. So not all you have to wait till they contract, but um, yeah. At some
yeah,
point, though, they should some of them become UV emitters.
yeah, but not this one.
Yeah. Yeah.
Yeah,
Well, then over the years, people have wondered. I mean, certainly in our group, we've been wondering: is there dust in the outflow, and which components? So, do you can you tell from, I don't know, the continuum of the jet knots or the outflow whether they contain dust grains?
yeah, we've gone a little bit back and forth on that a bit. I and if there is, it's subtle. And I think part of the reason it's subtle is that you think about a dust grain in a jet, it may not be that hot, right? Not necessarily, particularly if it's, maybe if it passes through a shock that can heat it, but it's actually getting far from the central protostar. So it's not going to be that hot in the Miri range. And in addition, if it could be scattered light, but it's hard to pick up that scattered light against the scattered light from the cavity walls. So detecting dust in the outflow jets and in the winds is a really interesting question, but it's very hard to do. And so we have tried a bit. We in some of the jets we do see molecules. We see like a blob of molecules in B335. HOPS 370, the northern jet has molecules. It has H2, both of them have H2, and if you are forming H2 in the jet after it's launching, as opposed to just launching it straight, then you would need some level of dust in the jet. But that's very indirect. So yeah, that's a really good question. It's something we've explored, but we just haven't been able to pull out yet.
Hmm. I mean, you showed some continuum emission, I think, from your spectrum of the
Yeah.
jet knot.
Yeah. Okay. Yeah. So this is the you're talking about the 383 data. Well, that A is super fresh off the press. And there is a little bit of a peak up here, but I'm not sure exactly how much I believe that. There is an issue with, well, we did subtract it from the side. I would be hesitant at this moment to say that it was, but it's something obviously that we need to look into.
Hmm.
Uh, yeah, but yeah, that would be really that might be a nice would be a nice example of that. So
Hmm.
yeah,
Right. We have about 5 or 6 minutes left for questions and so on. So are there other questions online or? Well, in terms of then I mean, you mentioned the ICEs at the beginning. I'm trying to see what you can be measuring from the ICEs now. So for example, the isotopic fractionation, can you measure that yet from the 13
yeah.
or CO?
Well, so the isotopic fractionation, we there is a paper by Nishanti Brunken for 20126 where we try to do the 12 to 13 CO. She gets a number roughly around 90. Um, Also, another thing that we have done is basically look at the H2O to H2O ratio. This is a work by Katie Slavinska, where you can sort of see very subtle HDO features in our data. And actually, one of the things with our NIRSpec data, if you're a NIRSpec aficionado, you know there's a medium and a high resolution mode. And the high resolution mode has a gap at around 4 microns, right where bracket alpha is. And so we use the medium resolution mode, which has additional problems, and that allowed us to measure the HDO. And so we managed to get, she did this sort of amazing work trying to pull out the HDO to H2O ratios for these objects. Here you can see the HDO measurements. And from that, and then the H2O you can get from the water ice feature. And you can sort of see that the HDO and H2O ratios that we derived for these two objects are sort of roughly consistent with other sort of class zero protostars and stuff. And this is now is being applied to lower mass objects and such. So it's basically being able to measure the HDO to H2O ratio in the ices themselves and not just in the gas phase.
Ah, so you do have quite good measurements here. I mean,
Yeah.
can you even do mapping of, because you sort of showed from the IFU data, maybe you have maps of the ice features. So can you spatially?
Yeah, that is an interesting question. I don't think we've. I'm trying to remember if Himanshu put the HDO to H2O ratio. I don't think we did the mapping because the HDO ratio is very subtle in this source, but you could. We did do the. If you actually go to his paper, there's fits in a bunch of ices, and I honestly don't remember if the HDO ratio is in there, but I don't think so,
Hmm.
because of its subtlety. But yeah, that's a possibility. You can do this at the shorter wavelengths because you have the scattered light nebula. At the longer wavelengths, you can't because you're basically limited to the thermal emission closer to the protostar.
Hmm. Hmm. Well, that seems
So,
a
but
great
yeah,
thing to be done here.
yeah.
Uh, Very good then. Any other questions for Tom? So let me see then. The wide angle wind that you showed and the connection to the jet. Then, I mean, the models I'm familiar with are the Matzner McKee sort of self-similar models, which have roughly equal momentum flux per decade in opening angle range. But I'm trying to see. You showed the mass flux in the
No, yeah.
jet was
So,
quite
so
low, but is the momentum flux? What is the momentum flux in the jet compared to the momentum flux in the wider angle component?
we're still working on that. At least for 62253, it seems to be lower in the jet in the wider angle component. But because we're having some issues with the jet modeling, right? Remember the shocked gas. So there are some assumptions here. So with the jets, we basically the shock gas is a small fraction of the gas in the jet, right? It's just when there's internal shocks, and so you need shock models to get flow rates and stuff. For the H2, we're sort of assuming that the warm and hot H2 is tracing all of the material. But that's actually, it could be more of a lower limit because there could be cold H2 that's just not being heated. And there's actually an additional question, which I think is a really fascinating one of what's actually heating the H2. It's not the thermal, it's not the radiation from the star, and it should cool off fairly rapidly. So I think there must be internal shocks in the H2 that's heating it. So why did I go into that? So just note that when we measure these H2 values, that's just all the warm and hot H2 in the cavity that we're getting that from, and assuming a sort of a given velocity. But there could be colder material in there that we haven't fully detected yet because we can't see anything below the S1 line.
But you're already finding that the wider angle is dominating, so that would only increase it. Whereas I think
I
the
think so. Yeah. I think somewhere the jets might be equivalent. We played around with this with earlier numbers, but because our jet numbers are suspect at the moment, um, we're not really at the point of publishing it. But sometimes it's the winds are at least equal to, and I think dominate, at least equal to or dominate the jet.
Mm-hmm.
Now, the imaginary Bikey models are effectively X-wind models. They assume a constant velocity at all angles, from what I remember. And so that's another thing is our wide angle component is a lower velocity, right? And so it's not just, and so that's sort of seems like a more of a disk wind model where the launching points, you're launching further and further out in the from the disk, and that would be a natural explanation why you have molecules as well in the wind. So you're just launching molecular gas.
Well, I think those models can generalize to both the disk and X-winds, but yeah, we'll have to go back and check.
Right, right. Reality may be a mixture of the two, right? So there's no reason why you have to have one or the other.
Right.
Yeah.
Very good then. Well, we're almost at the hour here. So any last burning questions for Tom? Otherwise, we'll have a more informal discussion in a moment for those who want to stay in. But not seeing that, let me close the formal recorded session by thanking Tom again for a great talk and discussion.
Right.